Today's lecture is about the reservoir fluid properties, and we will see what kind of fluid properties as a reservoir engineer we need to know and why, what kind of properties are available, and so on. Now, first of all, we have to look at the composition. When we talk about the reservoir fluid, what is the composition of the reservoir? What exactly is coming out of hole or coming out of reservoir? That's the first thing we need to know is composition, chemical composition of that reservoir fluids. Then the second thing is phase behavior. This is the most important part of reservoir engineering, especially when we talk about the fluid behaviors. So this is the most important part. Then we talk about the properties of gas and oil that we need to know and so on. And we look at some experimental analysis that we do. First of all, why we need to know about the fluid properties? The first question is the volume of hydrocarbon initially in place. Can you see both these screens? I have one presentation as well as I have whiteboard. Can you see both of them?
Yes.
Okay. Because I want to see from here and put it here. Now, for example, we have the reservoir, something looks like this one. And then we put the well into it. Let me erase it. It looks like this with the same string. Now, we want to know the reservoir fluid properties. The first thing, why? Because we want to quantify this area. Whatever is this area is, we call it a pay zone or the reservoir or the fluid reservoir pool. So we have to actually find out exactly how much oil it has inside. In order to know that, the first thing is important is definitely the rock properties, but also at the same time, whatever the fluid we have here, we need to know certain properties of it also. So what properties, we will discuss them. But for now, in order to quantify the amount of oil inside the reservoir, we need to know the fluid property as soon as possible. The second thing we want to know is reservoir fluid properties, is because we want to know how we can develop a reservoir. What does it mean that by developing the reservoir, basically, it means that how many wells you are going to put and where exactly you are going to produce from. For example, this well, or you can put this well, or you can put this well, or you can put like 5 wells here. Like how many wells you need to put in this reservoir and exactly at what depth. So in order to find the total number of wells at one place in one reservoir, we need to know again the fluid property. Okay. Behavior of the reservoir during production. This is another most important parameter. Reservoir has life, as we have. Okay. It is continuously changing. As you are producing, the pressure is declining. And as the pressure is declining, the composition of the fluid is changing. And many other things are changing inside the reservoir. So it's a dynamic process. The reservoir is not static. It's not like same what you see today. Maybe after 1 year you come back, you see the same reservoir with same composition, with same properties. No. The properties of the reservoir fluids are changing continuously. So usually most of the properties are dynamic. That's why as a reservoir engineer, we keep and track on them again and again and so on. That's why we want to know the behavior of the reservoir. Then the another story here is the recovery efficiency. Exactly how many % we can recover by having the best developing strategy so that we can have the most of the oil out of it. Now to improve the recovery efficiency, we need to know what kind of fluids we have. Has it more gas? Has it more oil? I mean, what kind of reservoir fluids we are going to produce. So in order to have that, we need to know the reservoir fluid properties. And the surface facilities, again, it has to be designed based on the reservoir fluids. For example, now we have the reservoir. Again, I draw a picture like this one. We have the well here. This is the simplest explanation we have for Christmas tree. And now we have this kind of one. Now, if we are dealing with the oil reservoir, the separator, whatever separator we are going to put here, whatever separator we are going to have here will be different. If we are dealing with lots of gas, then we have to, and also, for example, you have producing oil, you have to arrange the transport for it or pipeline, and you have to arrange the storages there. Maybe you need a few storages so that you can store the oil that is coming out of the well. So all your facilities here, this is the storage one, the storage two. So you need to design your storages as well as your separator, as well as your surface facilities, as well as your transportation mechanism, all based on how much oil you are getting here. Sorry. Now, in this case here, for example, we are producing, and we are talking about the oil reservoir here. Oil reservoir. Now, this oil reservoir, so that we have storage, oil is coming out, we are storing it, and so all these facilities are based on this oil reservoir. But what if this is not an oil reservoir? It's a gas reservoir. Okay, it's not. It's not. It's a gas reservoir. So it means that we are producing the gas. Now, if you have the gas reservoir, then what storage are going to do here? Because these are the oil storages. So you are not going to need the storages here because you are dealing with the gas reservoir. So you don't need the storage now. Okay. So what you will do, you will send this gas to the storage gas processing plant. Gas processing. Okay, and gas processing also has its own cost. So all these factors actually, that's why we must know the reservoir fluid, what's going on with the reservoir fluids. So when you go to the oil and gas field, okay, the first thing you should look at it, what is the composition, what you are exactly getting out of the reservoir. Whether it's water, for example, now this is gas reservoir, water support. Okay, it is supported by water. Means it has the water underneath it. Now, if you have the water is also coming out, it means that you have to now settle down the produced water. And this produced water is toxic. So you need to look at it like what kind of fluids are coming out. So you design your surface facility based on the facilities, the fluid composition you are getting. That's the whole idea of this reservoir fluid properties. Okay. Now let's look at first the composition. We discussed again in the first chapter that it consists of paraffin, naphthalene, and aromatics, these three ones. But now let's look at closer what exactly is going on. Okay. In the reservoir, we could have methane, ethane, propane, butane, pentane, hexane, heptane, octane, and nonane, and decane. C1 to C10. So this one, sometimes we call it C1 also. This is C2, C3, C4, C5. When we talk about the engineering studies, we represent them as C1, C2, C3, C4, and so on. As the number is increasing, so on. So the question probably in the midterm can write down the typical hydrocarbons which are produced from the reservoir. So you need to write down from methane to heptane and so on. Okay. And what kind of non-hydrocarbon material we are producing, fluids we are producing, mostly carbon dioxide, nitrogen, hydrogen sulfide, and helium, and so on, and oxygen sometimes, and so on. Now, this was the general introduction of the composition that we are receiving, methane, ethane, propane. Now, for example, as I showed you in a picture, that we are dealing with the gas reservoir. So what do you mean by the gas reservoir? Gas reservoir means that we are producing mainly methane and ethane. So now 90% in the gas reservoirs, actually the methane or ethane is produced. Okay, that's called the gas reservoirs. But if you go for the next one, which is the oil reservoir, for example, crude oil fractions. Okay, here it is. Yeah, if you go for the oil reservoir, this pentane here is 3%. Pentane should be 70%, 50%, 60%, and so on. So pentane and actually pentane plus products are called liquid product, liquefied products on crude oil. So pentane onwards, whatever composition it is more is called the oil reservoir. So oil reservoir basically have pentane, hexane, heptane, octane, and very less amount of methane or ethane or propane. But on the other hand, the gas reservoir has main constituents as methane and ethane, and very less amount of pentane, hexane, heptane, as shown here, 3%, 2%, or 1%. But if it was oil reservoir, it should be 30%, 40%, 50%, and this one should be 10%, 5%, 20%, 25%. So we call it an oil reservoir because there's no methane, ethane, but we have a lot of pentane, hexane, heptane, and so on. So you will see the question like what are the typical hydrocarbons composition and write down the typical gas reservoir composition. So this is the typical gas reservoir composition. What is a typical oil reservoir composition? Just opposite them. Okay, put 3% to the methane, 45 to 92% to pentane, 4 21% to ethane. See, he put here that one 4 to 21% here, and they remain the same. They could be with oil reservoir, they could be with the gas reservoir, as low as possible. Okay, now we need to look at further that what kind of products we are going to get from these fuels. As I said before, we are going to get the motor fuel, we are going to get the jet fuel, we are going to get the diesel, kerosene, and lots of lubricant, engine oil, cosmetics, petroleum jelly, waxes, tar. Yes.
I only see the whiteboard.
Wait. Here. Now can you see?
Yes, thank you.
Okay. Actually, you were late. I don't know what I was talking for the last 5 minutes. So let me get back to what I was trying to talk. Okay. Now, as I said that in the reservoir, we have two main kind of reservoir, gas reservoir or oil reservoir. And typical composition that we receive from the reservoir is methane, ethane, propane, butane, pentane, hexane, and heptane. When we talk about the gas reservoir, basically the gas reservoir has major part of methane and ethane. So you see here the methane is 70 to 98%. Ethane is 1 to 10%. So the major part of the gas reservoir are composed of methane and ethane gases. And the one which we are using at home, which is the propane and butane, is also considered as in the gas reservoir. But when we talk about the oil reservoir basically starts from the pentane, hexane, and heptane. When the pentane, let's say you are producing 40 to 50%, then you can call it an oil reservoir. Okay. So the question may come in the midterm or final that what is the typical hydrocarbon composition in the reservoir, and write the typical gas reservoir composition. So this is the typical gas reservoir composition we are talking about. But when we talk about the oil reservoir composition, basically it means that we have higher amount of pentane, around 50%, 60%, or hexane, or maybe heptane, and so on. And we have a lot of non-hydrocarbon amount, also nitrogen, CO2, H2S, helium, oxygen, and so on. These can be in oil reservoir, this can be in gas reservoir, traces can be 1%, 5 to 5% to 10% even sometimes, but not a lot. But we need to remove them also. But this is the composition that I'm talking about here. The another thing I mentioned here that methane, ethane, propane, butane, whatever, we use in the softwares or calculation usually the word C1, C2, C3. So usually when I talk about, in any course, okay, we are producing C1, so it means that we are producing methane. When I say, okay, now our reservoir is producing mainly C5, so it means I'm talking about the pentane. What is the difference between all of them? Their heating value. Methane well has the least heating value. As you go down, the heating value is increasing. It means it has more capacity, energy to burn, energy to produce heat, all of them here. So that's the typical composition. Okay. Now, when we talk about the crude oil, mainly it is composed of carbon, 84 to 87%. Then it should have hydrogen bond and sulfur, nitrogen, and oxygen, and so on. This is the typical composition. So, as a reservoir fluid, what we have: methane, ethane, propane, butane, hexane, heptane. What amount we need to know. And if you go to any oil field, okay, any refinery, the first thing you need to look at it, what exactly you are producing, what exactly the composition they have, how much methane they are producing or how much pentane they are producing. So whether it's oil reservoir or the gas reservoir, this is the first thing you need to know there when you go to the there. Also, we have other components of these reservoir fluids. One of them is sour gas. So when the reservoir has the fluids contain the H2S gas, H2S is a very acidic and toxic gas. It can even kill people. It can make unconscious. So we don't want this H2S, and it's a very toxic gas. So as long as the oil reservoir gas has the gas reservoir has the H2S contained, we call it a sour gas. And if it has no H2S, it's a sweet gas, means it has no toxic acid gases and so on. So acid gas, as you see here, contains CO2 also. So CO2, H2S are not desired. We don't want them. They are useless. But on the other side, they are environmental and health hazard. They have lots of environmental and health hazard, and we don't want them actually. Also, there are the solid particles that we have in the crude oil. These are called asphaltenes and so on. These may come out and make us stones and cause a lot of problems in the reservoir. So asphaltene, we will talk about it later on in much detail. So now as a typical composition, if you can, in conclusion actually, you can actually say that the reservoir fluids, there are 10, basically starting from methane, then there could be ethane, propane, butane, hexane, heptane, octane, nonane, and so on. And the oil reservoir, it could be oil reservoir, it could be gas reservoir, and so on. In oil reservoir, main components could be pentane, hexane, octane, and in gas reservoir, the main components could be methane, ethane gas. Okay. Now, after this composition, the next most important part of reservoir engineering, I would say 30 to 40% reservoir engineering consists of the phase behavior evaluation. Now, before I start the phase behavior, I would like to tell you that, for example, now you have your home, and you should know that before you build that home, you should have a map of it or architecture plan of it. Okay. Now, if you design any building in anywhere here, it should have its own map or architecture plan and so on. Likewise, that the buildings have their own plans and everything. Even for our course, for example, if you look at it, we plan it very well, and we have a complete syllabus where everything is written about those about our course, that what we are planning. For example, today's lecture, if you go back, you can exactly find out that today's topic could be reservoir fluid properties, and we are dealing chapter 3 right now in this week. It's already written in syllabus. So now we have, it means that we have a complete map of our course at the same time. Now, similarly, when we talk about the buildings or our syllabus, the reservoir also have their maps. Okay, and we talk about these maps in terms of the phase behavior. Okay, so when you go to visit the reservoir engineering office or any office, you will typically see diagrams like this one. Okay, so we call it actually the phase diagram. This diagram basically explains us the reservoir, what kind of reservoir we are doing, whether it's an oil reservoir or whether it's a gas reservoir. We can find out from this chart whether what is the current condition, current pressure, what is the current temperature. We can exactly find out the reservoir condition. Okay, further we can find out more, for example, how much oil is left and or how much gas is there inside the one at this point. Okay, so this phase behavior diagram actually is an architect of the reservoir fluid in the reservoir. So reservoir fluid is usually we represent this using this one. Okay, now in order to construct this, we need some properties. We can find out this one, and we have a software called PVT analysis, PVTP, which develops this kind of one. We are going to get this software also soon, so you can actually develop these phase diagrams there also. Now, this was till right now, I was just explaining that, okay, we have a phase behavior diagram. This is an architecture of the plan of the reservoir fluid. It can tell us what kind of reservoir we are dealing with. and it can tell us the reservoir properties, like exactly what is the current condition of the reservoir. Now I will describe this phase behavior in more detail, exactly what's going on in this one, in this chart, Okay. Now, in order to explain this chart here, I will put one line usually. Something like that. Okay. Now I will put another line actually, and I will say that okay, two lines. So when you will go to the reservoir engineering office, you will see a chart like this one, exactly what you see here. The shape can be different because like the shape of this reservoir, uh, every reservoir has its own shape. Every reservoir has its own composition. So every reservoir is as different as the human faces. Okay. So when you look at the phase behavior or phase diagram, this is a very general phase diagram you see here. Every reservoir will come up, a different phase behavior and different diagram like this one. Okay, maybe this line the line would not be like them here. The lines will be different, but by looking at it, you can find out it's a phase diagram because in general, all should look like this one as you see here. But of course, it will be different in its shape. Now, when you go to the reservoir engineering office, you will see that they will have two lines. Okay. Now this line, oh, here it is. They have already put one line here. Here they have two lines. One is this one, okay, and one is this one. Now this line, when we put it actually represents the current reservoir pressure and temperature. For example, here you see we have the pressure. The y-axis here is pressure, and the x-axis here is temperature. So when we put this line here, basically, so it shows exactly what is the current temperature of the reservoir. Okay. If I extend this line, okay, this shows what is the current, maybe the current temperature, let's say 70 degree or 80 degree. So we will set up this line at 70, 80 degree, and this tells us, by looking at it, we can say, okay, the reservoir right now we are dealing with, its current temperature is 70 degrees. We can find out very easily from here. The other thing which it points out is its current pressure. What is the current pressure? As I said, the reservoir life is different, and now if you look at it, if the line is here, let's say in the beginning of 2000, let me do the whiteboard actually. I will try to make a similar kind of. And we have here we have the temperature, here we have the pressure. It should look like this now. This is, we call it a phase diagram of the reservoir. So it's a diagram talking about the phase behavior, what exactly is going on. Now, as I said, when we know that the temperature of the reservoir, we find out exactly from the crude oil temperature exactly what is it. So temperature, let's say 70 degrees. We will put one line here at 70 degrees centigrade. 70 degrees. Okay. Now we have another line. Now this line is changing. As you know that for example, if you are producing some reservoir exactly in 2010, its pressure probably is 2000 psi. But the same reservoir, if you're producing in 2012, the pressure may decline to 1900 psi. If you are producing in 2014, let's say, the pressure declined further to, let's say, 1800 psi. Now we are producing in 2020, the pressure has declined to 1200. Okay. Now this 2000 psi, probably you can represent this actually at this point. At this point, you can represent at this 2000. Okay. Now, as I said, for 1900, maybe situation is like that. Or if you have, let's say, the 1800 or 1200 psi, maybe 1200 is like here. Now, when we look at the situation here at 2000, or when we look at the situation here as 1200, reservoir shows a very, very different scenario. In this case, we have now, let me go back to the another one. I will clear this for now, or maybe I will come back there. Okay. We have basically three kinds of reservoir: undersaturated reservoirs, saturated reservoirs, and condensate reservoirs. Basically, let's talk about these two ones: undersaturated and saturated. Okay. Anyone has an idea what is undersaturated and saturated reservoir? Anyone can tell me? Anyone? Okay. The undersaturated reservoir, if I define it here, it means that the reservoir has only one phase, which is liquid. Okay. Now, where we can find out this in the phase diagram? I think I cannot go back to the old one, but I will show you in the previous one. So we have two conditions, as I said: undersaturated reservoir and the saturated reservoir. Second one is the saturated reservoir. Saturated reservoir means the reservoir fluids are in two phases. Phase one could be gas, could be oil. Two phase. Now both conditions exist in the, as the pressure declines, we are moving. As the pressure is declining from, let's say, 2000 to, we define it with the nearest by the bubble point, actually, where the first drop of bubble comes out. Let's say this pressure is defined as 1850, and here let's say 1200 psi. So at this condition, basically the reservoir was single phase, and at this condition the reservoir single phase, but first drop came out. Yes. At 1200 psi is exactly the two phase, oil plus gas. So now, by showing the illustration of these three, or these two, or these, I wanted to explain that as the reservoir pressure declines, we are moving from the single phase to two phase. And if the reservoir pressure, the reservoir fluids are above the saturation pressure, above the bubble point, they represent the single phase. Now, if you go back to the slide and from this point, okay, till this point where this line starts, the liquid line starts, if the pressure is between here to here, the reservoir is under saturated condition. And as you see that I put the line here, it shows that reservoir is only single phase. So what production we are getting is mostly the oil, not any other. The reservoir is actually a single phase, and mostly we are talking about the oil. And the reservoir has not achieved the bubble point. It means the gas has not came out in the reservoir. The reservoir mainly is oil. This is the first thing. Now, as I said, the reservoir is dynamic and is alive, and situation is changing every time, every moment, every day situation is changing, pressures are changing. And usually we are always in a declining phase. It means that pressure is always declining. Pressure will never go above whatever we have once we have. Like the life of the human is always, increasing. So it cannot go in a reverse direction. Like the reservoir pressure, unless, earthquake happen and some other support comes in, there's no chance that the pressure will increase. Pressure always declines. In this case also pressure declines. So when the pressure declines, in this case here is single phase undersaturated condition. But when the pressure declines, this can come in a zone. Now maybe here we have different situation. Here we don't have a single phase. Here probably we have oil, which is around, you can say 60%, and 40% probably it represents the gas here at this point. There's a critical point also. So this lines actually X and Y, the pressure line and reservoir line, the temperature line exactly tell us what is the current pressure and what is the current temperature of the reservoir. This is the first thing. Now let's look more in this graph, what more we have here in this graph. We have two lines here. Okay, this is the liquid line and this is the dew point line, is the vapor line. So if the reservoir temperature here, if this line is here, it means we are dealing with the gas reservoir. If this line is below the critical point, this critical point crosses the tear, it means it has some oil. How much oil depends on the pressure. So we basically play with the both line, temperature and the pressure. And both are, as I said, as the life of the reservoir is progressing, the pressure especially is changing. Temperature probably remains the same, but the pressure exactly is changing a lot. So this line actually tells us what kind of reservoir we are dealing with. And this line also tells us exactly, by matching these 2 points here, for example, we can tell how much oil we have in the reservoir and how much gas currently we have in the reservoir. This is the two things that we need to learn. Now, this was the general explanation of the phase behavior. There's something more in this chart. First of all, we need to understand what are these 5 points. We have points. We have, let's say, this point here, this point. We have, let's say, this point. We have here this point. Okay, and we have this thick black line, and then we have this big thick line. So there are 5 different points that we need to understand what are those in this graph, and which also you will see as a question in the midterm exam. What is the phase behavior? Draw a typical phase behavior. Describe what is bubble point pressure and dew point line. What is criconin thumb? What is criconin bar? What is critical point? Let's start from the critical point. What is the critical point? The critical point basically is the point where properties of all the fluids, they are same. As you know that, for example, if you want to convert the gas to the liquid, if you make it under very high pressure, the gas will convert to the liquid. It will change its phase. But there should be a point exactly where it will start changing. So that is called the critical point. Okay. For example, to pass a course or to fail a course, how much is the passing criteria? 65 in AUIs or 60?
60.
60. So to pass a course, 60 is the critical point. If you go above it, you are passed. If you go below it, you are failed. So that's the critical point. Likewise, that critical point, every fluid, whether you are dealing with pentane, hexane, pethane, ethane, propane, every fluid has its own critical point. Above it is a liquid, below it is a gas. Okay, so that's the situation and phase of that liquid or gas, that critical point. We have to mention it here. And this critical point is based on the reservoir fluids of the reservoir. And as I said, every reservoir is different. And as I always say, reservoir is always right. We may be wrong, but reservoir is always right. So whatever is the reservoir composition, it has its own critical point. We check it in the laboratory and we put it here. It means that if we go above it, it could be liquid. If we go below it, it can be a gas at that point. Exactly like your passing criteria, you have 60. If you go above it, you are passed. If you go below it, you are failed. So it's a critical point. Then we have 2 more lines here, liquid and the vapor. Now, for example, when we are dealing with the this one liquid line, bubble point line, it means that if the pressure is above it, it means we are dealing with only liquid. So anything above this thick line is a liquid in the reservoir. But if the reservoir, let's say condition, temperature, let's say the temperature here, situation is something like this. Now, if the both points are meeting at this point, it means we are dealing with a pure gas reservoir, because this line, vapor line, shows that anything out of it is a gas reservoir. So we actually find out whether we are dealing with a gas reservoir or the oil reservoir based on, again, these 2 points, but exactly where they are located. If they are located here, we are dealing with a gas reservoir. But if they are located here, for example, above the critical point, okay, if you change below the critical point, it is a gas again. So above the critical point, it's a liquid above here. But as I said, as the pressure is declining, because if you look at here, the pressure above, let's say more here is less. As the pressure is declining here, we are shifting from the single phase to the 2 phase. How much 2 phase this phase envelops actually tells us that story here. Okay. Now, what is the bubble point and dew point? So as I said, anything above it is a liquid, this from bubble point line, and anything below this vapor line, dew point line is a gas. That's what we know from the phase behavior diagram. Then further, we have the cryocoolant therm and cryocoolant bar. This is the highest pressure cryocoolant bar. Bar already represents the pressure. It is the highest pressure at which liquid and gas can coexist. I mean, this is above it, it will change its phase. That's it. It convert to the gas and so on. And this is the maximum temperature at which the properties can coexist in equilibrium. So we always define all of them, and we define our reservoir situation. What exactly we find out from these phase behavior is the current status of the pressure, current status of the temperature, current status of how much oil phase we have, how much gas phase we have, both of them. Okay, so this is basically, we are dealing with two-phase behavior. We are dealing only with liquid and gas here. But we could have a three-phase behavior also. That is more complicated, but we start from the two-phase to explain that. Now here you can see the bubble point. So for example, if the reservoir pressure declines from, here is the same thing is written here, P declines through P. So when P declines through B, it means the reservoir, the gas has came out of a solution. So any pressure line, this is if you put the pressure line and the current pressure is less than this B point, it means it should, there is always the gas in the side. It means now reservoir has gas as well as the oil. That's what it is trying to know. And this point here is the bubble point pressure. What is the bubble point pressure? Is the pressure where the first drop of gas comes out of a solution. We will talk about it in the property section and so on. Okay. So these are the points we find out. We find out the pressure, we find out the bubble point pressure, we find out the current temperature, we can find out exactly right now how much oil we have and how much gas we are producing. Based on this one, we find out, because our main concern is to produce the oil. So we want to minimize the amount of gas produced. So we have to look at the strategy, like maybe we change the perforation or areas where our wells are located. Maybe we try to change where the gas, why this gas is coming too much or so on. So we try to look at it like how much is the exact condition, so on, using this phase behavior. Now, we have different kind of oil reservoirs. Now, first oil kind of reservoir, we call it also the black oil reservoir, low shrinkage reservoir, in which the pressure is far away from the critical point, as you see here. The critical point is here. Then we have volatile oil. It changes, means it is also far away, but it can be gas, so produce a lot of gas. It can be oil. So this changes the situation of it. So because here you can see that even we are below the bubble point, but still we are dealing with a single phase. Even the line is here, below it, the 75% oil and 25% gas starts exactly so far from the main area. So here you can see. But here you can see that no, the lines envelopes are different. Now we are dealing with two phase after the bubble point here in this one. So this is the high shrinkage, means the gas can come out and oil can shrink and so on. Based on these values, we actually define our reservoir strategies, how to manage the reservoir based on these ones. Okay. So as I said, the reservoir oils are termed as undersaturated when we have only single phase. So when we have the reservoir above this B point is undersaturated, means we are dealing with single phase, which is the oil. Okay. But if we are dealing with the undersaturated or saturated situation, there's always two phase, which is gas and oil. So As I said, also it is written here, in an undersaturated reservoir, only liquid phase exists. No gas cap, no gas. Gas does not come out of a solution until the bubble point is reached. So this is called the undersaturated condition as we discussed. But in the saturated one, we have two phases. Now this is a typical gas behavior. You see now, as I told you earlier, that every reservoir has its own phase behavior diagram. So look at this picture, look at this picture, and look at this picture, and look at this picture. They all are different. They all are different because they represent a different reservoirs and so on. So that's why we have to find out exactly what's going on here in the high shrinkage. This is the reservoir. Now, in this case, again, we have to look at exactly where is our current pressure and so on. And same things is mentioned here for the one. As for the dry gas, okay, we have a different kind of gas reservoir. We have reservoir which has the dry gas reservoir. We have reservoir kind of wet gas reservoir. Then we have the retrograde condensate reservoir. When we talk about the dry gas reservoir, it means we are dealing purely methane and ethane. It has no liquids. So when we are dealing with purely methane, it means that we are dealing something away from this vapor line. That's why you see line A and B, which is far away from this phase here, because we are dealing purely gas. It has no liquid. So it is, whether it's point A or whether it's point B, it's still a gas. So we call it a dry gas reservoir. And this kind of reservoir, it has nothing else, just the methane, ethane, or maybe some nitrogen, oxygen, and so on, but no liquid at all. But then we have the wet kind of gas reservoir. It means at initial condition, it's a gas. As you see at point D, it is a gas. But as we produce it, the pressure starts to decline. And when the bubble point or dew point is reached here at this point, two phases start. The liquid comes out, and now we have two phases here. So it still has some liquid component. That's why we call it a wet gas reservoir. Then we have the third one, retrograde condensate reservoir. In this kind of reservoir, the reservoir is actually changing its phase. First it's a gas, then it becomes liquid, then it becomes gas. So that's why we call it a retrograde gas condenser. It means it is producing oil, then this oil is going back inside the solution, and then it is turning to the gas again. So it's a bit complicated kind of reservoir because it's analyzing this kind of phase behavior is a bit harder than the other one. So that was about the phase behavior. Now, if you want to know more about the phase behavior, you can look at the book of Tariq Ahmed, and there you can find more information about the phase behavior and convection. So basically, I will end the lecture today here, and in the next lecture, we'll talk about the gas properties and so on. And we'll talk about what is the equation of state in the next lecture. We'll talk about the Z factor, basically. Do you have any idea about Z factor before? You studied in any other course?
No.
No, yeah, Z factor is a very important factor in reservoir fluids. We will talk about the Z factor here. And there are some more properties that we need to know, which is the formation volume factors. Again, very important concept. We have another gas expansion factor, and we have compressibility, viscosity, density. All of them, they have effect in the development of the reservoirs and so on. Oil formation volume factor, gas oil ratio, solution gas oil ratio, practicing gas oil ratio. We'll talk about them with the videos. I have animations, and inshallah, your concept will be very good in the properties and so on. So for today, we will just finish it here so that you can grab an idea, review on this weekend, so that in the next week, we will talk about oil and gas properties more. For now, if you get a concept of phase behavior, it is, for me, I could not understand during my undergrad degree. Even I tried a lot, I tried books, but nobody was there to explain me in a nice way. So, but now things have changed. We have YouTube, we have animations and so on. So if you want to learn more about the phase behavior, you can always just look for YouTube videos, animations. You can look at the book. Also, you can reach me if you are stuck at certain point and to understand the phase behavior. And as I said, you have to take every topic very serious in oil and gas, because you don't have any other course which is going to repeat this thing. So once it is gone, it is gone. So therefore, take care of the concepts, build your concepts as we continue ahead. That's why I'm taking care of the concepts. What I'm here for is to build your main concepts in oil and gas we are dealing with. Any questions?
Doctor, I have a question, please.
Yes.
Doctor, about the presentation, can you join us, remember?
Yes.
Is that okay? I mean, you have mentioned that it's only 2 people allowed,
Yeah.
but can we have like 3 members?
Okay, go with 3. I have no problem.
Thank you so much.
Most of in fact,
okay,
all the
thank you
students,
so
they
much.
are good. They are good. I have no problem because all the students are good in this class. So I have no problem.
It's okay. That's right. As you remember, at the beginning of the lecture, I've asked you a question about yesterday's lab.
Let's finish this course and we do the meeting. I will send you. Just send me an email so we do the separate meeting.
Okay. Okay. Thank you so much, doctor.
Okay.
Thank you so much.
Okay. So any other question? Okay. Just send me your email so I invite you for the Zoom meeting after this one so we can discuss.
Okay, doctor. Thank you so much.
Okay. Okay. So if you have any question, please you can write me. You can ask me in the next lecture. Also, you can email me. So we just keep talking about the subjects and also this is recorded. I'm going to upload it so you can have a look and see what's going on. Also, book of Tariq Ahmad is very good for phase behavior. First chapter talks about this in a very nice way. Have a look at it and see what it says. Okay, so have a good day ahead and see you.
Thank you, sir.
Thank you.
See you, sir.